Thank you. Good afternoon. Good to see you all here. My name is Cas van Cooten, and today we're going to talk about languages, programming languages, of course, but I wanted to start with a little bridge to languages in the classical sense of the word, because languages to me are really fascinating. Everyone, or mostly everyone, knows at least one language. Most people know two, especially here in the Netherlands. I think a lot of people know 3, 4, 5 or more languages. And the interesting thing is that languages are all related, right? They're like families in a big tree. You can see some languages are closer together, some are further apart. But that means that the more languages that you learn, the more parallels that you see between these languages, and that the easier it gets to learn new languages, the more that you know. And this is also true for programming languages. So a lot of people think that learning a new programming language is really hard, which it can be. It's not always easy, but actually every programming language is essentially doing the same thing, right? You're trying to achieve something programmatically. There's these constructs like logic statements, if else, whatever. There's loops in there, and this is kind of generic for every language. So the more programming languages that you learn, the easier it gets. And that's also a little bit a flash forward to my call to action today, which is learn as many languages as you can. I'm a big fan of modern languages, can also be ancient boomer languages like C. That's up to you. But yeah, that will be my key message today. Of course, we're not only going to talk about languages, we're going to put it into a perspective a little bit of offensive development. So I tailored it a little bit to my worldview, which is distinctly red. Also useful, of course, for anyone that wants to automate more in their life, including blue teamers. Little bit about me. I'll skip through this a little bit because we have a lot to discuss. But my name is Cas van Cooten. I'm a red teamer at a big bank you may know here in the Netherlands. I call myself a malware linguist because I really enjoy, as you may guess by now, learning new, especially modern languages like Go, Rust, NIM, and trying to apply that to the field of offensive security. So that's also what we're going to talk about today. You can find me on Twitter as well with some shitty memes mostly, but sometimes there's some knowledge sharing there as well. And I post some stuff on GitHub if you want some examples. So let's take a step back to offensive development to start with. I think this situation, if you're in offensive operations, is all too familiar by now. I think over the last couple of years, probably 5 or more by now, we've seen this kind of the race between red and blue, right? And this is not new. This has always been there, but especially in the area of OST, offensive security tooling, or open source tooling, depending on what your definition is. This is very relevant because there's great tools that get published all the time. You can grab them off of GitHub and run them on your client's network, and you will have a bad day because, of course, the blue team is not sitting still, right? They are also looking at these great tools and making sure they are fingerprinted. So to use these tools in practice, you need something of a development capability. So the kind of least you can do is modify it, but there's other options as well. Essentially, there's 3, and this comes down a little bit to a business decision, because as a red team, as an offensive team, you get the choice here: how much do you want to do, or how much do you want to pay? Essentially, so the first option is to purchase your offensive tooling. I think more and more we are seeing offensive security companies step up and offer tooling that you can use, which is kind of evasive by design. So you're kind of paying money to get tooling that works in practice, right? You don't have to change it anymore. There's commercial C2 frameworks. You have whole toolkits like Outflank is offering now, for example. And yeah, you get all these options that you can essentially procure, so you don't need to do it yourself. Very valid option. You can also choose to adapt the tooling. That's essentially what I just mentioned. You have open source tools, right? They work well, but they are fingerprinted. So if you modify them to get rid of the fingerprints, you can use them again. The downside of that is that it's, well, there's still some behavior in there that you may not completely understand because it's not your tool, right? The upside is that it saves you a lot of time, development time, essentially. And the last option is actually what we're going to focus on today, which is to develop your own tools. Developing your own tools is my personal favorite because it's a lot of fun, first of all, but also it gives you 100% complete control of what you're building, right? That makes sense. But from an offensive perspective, that also means you have full control over the IOCs, the indicators that you're leaving in a client network. You have full control of what you're actually building. Of course, the downside, again, is that it takes the most time. But yeah, given the fact that it's a lot of fun in my experience, I would definitely recommend going there. So when I say offensive development or development in the context of offensive security, a lot of people immediately assume that I'm talking about malware development. But in my view, those two are a little bit different. I would actually say that malware development is a subset of offensive development. For the reasons that you see here, of course, offensive development encompasses everything that's used to support in offensive operations, right? And malware development I would define as everything that runs on your target system. Of course, the latter, malware development, is quite a different ballgame because there you're dealing with these defenses, you're dealing with EDR, you're dealing with network controls, all these kinds of things. So developing for on-target operations is quite challenging. But there's more to it. So if you look at some of the examples here, you can see that a lot of supporting tooling, even like the knowledge management or the scripts that you use to automate your offensive operations, these are all part of offensive development. So I wanted to mention that just to set the scene a little bit for what we're gonna discuss later. And one other thing that I wanted to mention before we actually get to the programming languages is the development part of offensive development, because we hackers are very known to kind of sitting like a monkey behind a keyboard and putting out some code that's like POC code, right? A lot of GitHub tools that you see actually have a disclaimer that says, this is a POC. I wrote this in one night. I was drunk, whatever. Don't run this in production. And then everyone takes it and runs it in production, right? So of course, working code is better than perfect code. But I would argue for a little bit more of a developer mindset in the field of offensive development or any development that we're doing in the context of security. Because bad code or maybe a code that you wrote very quickly or whatever, has a real impact. First of all, it can bother other people, right? If you're, for example, publishing your code, on GitHub, or you're collaborating on it with colleagues, and you have like one big chunk of code in one file that's not annotated. There's no comments. The variables are named very specifically, or you have like I, J, X, Y, Z. Then everyone reading this is like, oh, what's this? And maybe if it's open source, people decide not to maintain or not to contribute to your project because it's not readable, right? This is very easy to avoid. It just takes a little bit of a mindset while you're programming. Stability is another concern. This is usually for malware or like POCs. This is not a big problem. But when you're writing on-target implants, for example, C2 implants that need to run for weeks or months, maybe years on end, you really don't want a memory leak in there or some oversight that causes it to crash at a random time during the year. So that's a real concern as well. And finally, of course, we are security professionals. Bad code also impacts security. Now, a small disclaimer here. I don't want to shit too much on Paul, who is the maintainer of Havoc, because that's actually an excellent project. This is just the last example I could find of vulnerabilities being in security tools, open source security tools in this example, but it also happened to Cobalt Strike, for example. it's funny that we are security professionals, right? But the moment we start coding, sometimes we kind of forget the principles that we teach to others all the time. So like of course, you know all the web vulnerability stuff, but there's much more to it. And I think proper dev practice also means that when we are developing something, we should be really conscious about what we're doing, who's going to be able to communicate with it, will someone be able to intercept that traffic and abuse it, stuff like this. The good news is that it's not really hard to adopt this developer mindset, as I call it. It takes some maybe getting used to, some switching, but it's actually it's just a couple of principles that can really help you get a long way. There's a couple of principles like, of course, commenting your code, structuring it well, depending on which language you are using, and trying to minimize the repetition of code. Just a couple of principles can already help you really elevate your POCs to the next level. There's a couple of books as well. I particularly enjoyed this one, which are interesting to read as a security professional, because they kind of take a step back and go through these concepts that can really help you put the developer in offensive development. And I also found that AI, so Copilot or whatever AI assistant you are using, can actually help a lot here. There's a couple of prompts or a couple of keywords like idiomatic code that if you ask it that, it will come back and kind of get all the knowledge that it took from the Stack Overflow geeks and dump it on you, which is actually really good when you're learning a new language, right? Because you may be used to some low-level language and suddenly you're programming something in Python, and all these idioms, so the practices in that specific language, are very different than you're used to. So having AI kind of look over your shoulder, be very pedantic about the style that you use, the structuring of your code can help a lot. So let's actually get into the programming languages then. Also there, when choosing a language for your offensive project, I think we can just look at what normal developers are doing, right? On the right here, you see the Stack Overflow developer survey, which is like a yearly thing that they do where they ask which programming languages do you currently use, which is like the blue lines here, and which ones would you like to use in the coming year, which is the red lines over there. It's quite interesting to look at, honestly. They have a lot more questions as well, so I would recommend looking at that survey online if you have the chance. But there's a couple of trends that you see. For example, Rust, of course, being hyped as always. Python is the number one that's I think for many years now, and that's very relevant for us security professionals to know as well, especially when you're writing on-target malware. We've seen this with NIM, for example. If no one is using the language legitimately and suddenly like this suspicious binary pops up that's written in NIM and it's doing some weird allocations, then antivirus is just like, get out of here, because that's not going to happen, right? So the prevalence of a language actually helps in evasion. But of course, every language has kind of intrinsic design principles and elements that also make it relevant to choose as an offensive practitioner. A couple of considerations. I think one of the main considerations for offensive development is whether the language is interpreted or compiled. So interpreted means that there's like a interpreter that you need on the system already to read the code line by line and execute it. Python, I think, is the most famous example here. The downside is that the portability of the language really dives because you need to have that interpreter on the system to do anything. The upside is if the interpreter is on the system already, it's great. If you're doing off-target operations, this is great because the interpreter can really help you get started quickly and hit the ground running, so to say. Compiled, on the other hand, means that when you're done coding, you compile an artifact, so like an executable for Windows, for example, ELF binary for Linux, whatever, and you can take that, drop it anywhere where it's compiled for, and just run it. This is usually what you would do for like actual malware development. You would choose a compiled language because you're not dependent on that runtime, right? Very important as well is the language high level or low level? Now this is a bit vague, maybe hard to define, but in general, a language kind of intrinsically gives you some level of abstraction, right? I think Python probably is the most famous example of a very high level language, meaning that there's a lot of abstractions in Python that make the code very readable. Sometimes Python almost reads like natural English. But the abstractions mean that you're typing that and you're not exactly sure what's happening under the hood, right? The opposite of that is low level, where you're essentially giving the computer literal instructions almost in computer language. This is what happens in C, right? Or even assembler, where really like you have to think about what's the computer doing, and it's not abstracting anything for you. It's literally doing what you're saying, which brings a lot of risks as well, like safety in C is a big topic now that Rust jumped into. But yeah, it's a consideration depending on your product that matters. Performance. In my experience, performance is a little bit less important for most security tooling. Usually, unless you're writing like a highly concurrent port scanner, for example, we really don't care that much about performance, where normal developers would care a lot more. But still, if you're writing a project that does care about performance, of course you need to factor that in, because some languages are less performant than others. And it can also really differ per use case as well. Portability, already mentioned compiled languages where you just get a binary and can drop it somewhere. I also consider cross-compilation to be a part of this, where you can sit on Linux, compile something for Windows or for macOS. And I think especially modern languages are very good at this, where, for example, in Golang, you write your code. If you don't use any OS-specific libraries, then you can just compile it for whatever, right? NIM also did this. I think they natively offered support for, what was it, the Nintendo Switch or something like that. So modern languages are good at this, but of course you need to keep it in mind and consider if it's even relevant for your project. Then the prevalence, I think I already discussed this at the start of this slide. Prevalence essentially means how much is a language used. The more it's used, the more it will blend in. Simple as that. And finally, I also put developer experience here, which is an often overlooked fact, because people are like saying, oh, Rust is the new fastest language, or no, everyone's using C, you should use C. But when I code in C, personally, I become very unhappy. So that's essentially what developer experience means, right? Is there a good community? Is the compiler helping you fix your errors? Again, AI is now a part of this as well. So essentially, how do you feel when coding in a certain language? This is arguably maybe the most important option when choosing a language. Maybe it doesn't really matter to you. That's also fine, but something to consider before choosing a language for sure. Typing, meme intermezzo here. Typing is also part of a language. For those who don't know, typing essentially means that you're telling a language what type you want a certain variable to be. That's sometimes it's optional. Like in Python, you are allowed to define types. It's not always very strict. Some languages are very pedantic about this. But I think it's nice because exactly this happens, right? Where you're coding something and you do something weird, where suddenly a string enters the production line of integers, and then in the former case, your IDE or your text editor can already tell you, hey, there's something weird going on here, right? And sometimes people just code something and it's like, oh, I guess we're doing strings now. And when you run that on a target, it will do silly things, right? So typing also something to take into account. So how do you actually choose a language? Well, definitely do not use this decision tree, but it's like an example of your like a mind map that you could use to choose a language, right? You have all these properties that I just mentioned. You can essentially just Google them for new languages, like, okay, how performant is Go? And you will get a lot of people saying, oh, Rust is better. And then, okay, you look into Rust, and then you get people saying C is better. So you get into this rabbit hole. But in the end, you could almost make like an Excel sheet, map all the properties, find the ones that matter to you, and Bob's your uncle. That's the language you will use. Of course, there's a strong level of preference there as well. But in very high terms, I think the kind of the lower level-ish languages would be used a lot for malware development, right? Especially if you need all the control you can get, then this is the classical choice. I think this is the less classical choice for real malware development. But again, if you're writing something that doesn't need to run on a victim system, or it's not necessarily malware, then I think something like Go or even Python are excellent choices. So let's give a couple of examples of languages. Only have half an hour today, so I picked two. You can already guess that the first one is Rust, right? Because I did want to address some of the hype, what's true and what's not true about the hype. So Rust is it's a very interesting language, right? It's kind of jumping in the successor spot of C, even though C is still around a lot. Rust is trying to be safe C, right? So it's giving you all these tools, a very strong and strict compiler that's helping you write low-level code that's also safe. Now, the safety doesn't always matter that much for us malware developers, and that has some implications on the code that we write, because we will need to use a lot of unsafe clauses. But I think for anything else, it's really interesting, because that part about stability of security, Rust kind of solves intrinsically. It doesn't solve everything, don't get me wrong. It solves a lot of commonly made errors. It solves by using this mechanism that we call the borrow checker. The borrow checker is essentially just a tool that checks who is the owner of certain data at a certain time. That's like the easiest way to summarize it. Definitely won't get into all the rules of the borrow checker here. But what it means is essentially at compile time, or if you're using linters or whatever, then even before, it will look at who's the owner of certain variables, and if it's not moving in a way that it shouldn't be. So it's not being accessed by another function that's not the owner of it. There's no race conditions about the data. All kinds of stuff like this are being checked by this borrow checker. We will have an example about what this looks like. Important to mention is that there's no garbage collection. So other languages like Go, for example, they have a garbage collector. So that's like a part of the runtime that comes in once in a while, checks, is this variable still used? No, cleans it up. But that borrow checker has a performance impact. So it's actually bad for real-time or embedded applications. Rust does not have that. So that's an advantage performance-wise. Another advantage is that it gives you really verbose errors. Like if you did something stupid, it will literally say you did something stupid here in this line at this character and fix it in this way. So a lot of those issues are usually fixable very easily. And it's very well adopted. There's a mature ecosystem. It's used a lot now. Here's some examples to get you started. The slides, by the way, with links are on my GitHub, if you want to click the links instead of taking pictures. So that's something you could do. One thing that I really liked about Rust is the fact that there's quite a mature linter, which we call Clippy. So Clippy has a pedantic mode where it gets like really uptight about everything that you're doing. I found that really nice when first developing Rust, because it also checks, are you writing well-structured code? Are you writing idiomatic code? Stuff like this. It really helps you pick up the language. So if you give Rust a spin, I would advise to use Clippy. If you're up for it, put it in pedantic mode. There's also easier going modes, but it really helps write the code. So here's an example. We will go through it part by part. In this example, we are not only using the standard library. This example is actually some code that shows a message box with OK or cancel a couple of times, so really basic. So we use the Win32 library. That's actually a Microsoft built library because, of course, they're also using Rust in Windows now. So that's quite mature. There's two variants. There's one that's literally just the API wrappers, or there's a more Rustified version, which is this variant. Then we enter the main loop, and there's a couple of interesting things happening here. So first off, you see the kind of error handling that Rust has. Rust has a very specific error handling mechanism where you usually return a result. A result can either be OK or error. And then at the end of the function, you return the OK. If it's not OK, you return the error. This doesn't look like much, but it actually allows a lot of like sub-functions to look at this result of another function and verify if it did what you wanted. If you're returning a result, you can also return upstream errors in this way by using the question mark operator. So it doesn't always have to be super verbose. It is sometimes because Rust is just a verbose language. And another interesting point is that everything in Rust is immutable by default. So if you want a mutable variable, a variable that you need to edit, you actually have to specify that it's mutable. Again, doesn't seem like much, but this has huge implications in the logic that Rust uses to check if you're not making a mistake. Then we go to the actual Windows API call. Again, we see the error handling. This time we have a result that contains an option. So an option is either something, some value, or none. Again, having this type just gives you the option to verify whether you actually got a result. It's a bit more sturdy than just using the none in value in Python, for example, in terms of typing. And then you see here you have all the OK results with a value, or you return the error, and that error would be handled by the question mark by the caller. Here's the dreaded unsafe block. I wanted to show that unsafe is not necessarily bad, right? Because Rust often gets ridiculed a bit in the malware development space, where the unsafe it's just one big unsafe block. But if you use it properly, it's just a contract that says, okay, here I'm becoming responsible for the potential unsafety of whatever I'm calling within. That's just what Rust is telling you to do, because in this block the compiler cannot guarantee safety anymore. So you need to think about, okay, is this the white variant? I need to give it a white string, right? Stuff like this you need to think about. So it actually makes it quite explicit. And then you have a standard match clause which returns the result. The other example that I wanted to give is Go. Sorry guys, I'm running a little bit over time here, but I'll take a couple minutes more. Go, I think, is very interesting because it's both really useful on the target system as compiled binaries, .exes, for example, as well as on the server. Go is very performant. It has a very good concurrency mechanism that we'll have a quick look at in a bit. It has a really good standard library. There's packages for everything that you can imagine. And the syntax is actually really simple. So I would argue that Go is almost as easy to learn as Python. And it gives you these advantages of a really portable and performant compiled language, right? Because Python clearly has some performance issues. And that's where Go is really valuable. So another example here, which we'll go through quickly. We see some packages being imported. You see the formatting, networking, synchronization. This is all standard library. So despite the fact that it has import, it means just that it's importing it from the standard library. So you don't need to install anything to use this. And then this code is essentially a very concurrent port scanner in just, I think it's like 30 lines of code. So what we're doing here is just, preparing the port scan, right? We're not doing any argument parsing or stuff like that. But the key goal here is actually the Go keyword, because with the Go keyword, that means you're starting a Go routine, and Go routine is Go's implementation of concurrency. Essentially, this call means that we're calling this function, which is this one. That we'll take a look at that in just a minute, and it's starting it concurrently. So it's just starting a background job essentially and continuing with the rest of the loop. So what we're doing here is starting 1024 instances of this scan port function. Now, to manage that concurrency, we're using something that's called a wait group. Essentially, it's just a counter that says, okay, we go up to 1024 in this case, and then whenever every instance is done, we decrement one, and in this wait call is just blocking until all the processes are done. So the actual scanner implementation is also really simple. One thing that I wanted to highlight is the defer call, which is quite nice. It means call this whenever the scope ends. So either when the function exits, we call it, or when an unexpected error occurs. So just a really clean way to do your cleanup, stuff like that, and also the cleanup in case of errors, which is not usually the case. And then you have the error handling, which can be quite verbose in Go. Usually you would see something like this, but the inverse. So if the error is not nil, then we do some error management. Other than that, this just scans a single port. So the result, again, in 30 lines is mmap for poor people. So that's actually all I had to say today. Again, the call to action would be please look into every language you can get your hands on, play with it, adhere a little bit as best as you can to a good developer practice, build your own tools, and yeah, remember that new languages are not as hard to pick up as the first language that you ever picked up. Thank you very much.